Welcome to Mr. Brown's Basement, a channel devoted to sharing the craft of repairing, restoring, and modifying vintage electronic gear, and other random stuff. Before I get deep into this Vectorscope, just a heads up. There are going to be some highly technical parts of this video. Please feel free to use the chapters to skip ahead if they're not your cup of tea. I picked up this instrument in Whitechurch, Stouffville, Canada. This device is intended to be used to troubleshoot and adjust vintage televisions. It's useful for black and white TVs, but where it really shines is with color TVs. Its 3-inch picture tube makes it look like an oscilloscope, but looks can be deceiving. Even though it's called a Vectorscope, it's actually two pieces of test equipment, one of which is a Vectorscope. I'll talk more about what a Vectorscope is later on. Let's look at the controls on the front. On the right, there's a pattern selector. Using this control, you can put dots, lines, or bars on the screen of a black and white or color TV. You may have heard of a dot bar generator. That's exactly what this is. On a black and white TV, lines help you adjust the vertical linearity of the picture. On a color TV, lines and bars help you adjust linearity, field convergence, and color purity. And along with the Vectorscope part that follows, also in calibrating the chroma demodulator. When color is adjusted on a color TV, it is sometimes necessary to temporarily remove a primary color from the picture. That is what the color kill switches are for. Then there are controls to set up the Vectorscope, including intensity, focus, and horizontal and vertical position. These are used to put a sharp, bright dot in the middle of the screen before the Vectorscope is used. As mentioned before, this instrument looks just like an oscilloscope. Let's understand what an oscilloscope is, and then use that to understand a Vectorscope.
In the simplest sense, an oscilloscope is a voltmeter. I'm going to apply about 5 or 6 volts, and there you go. And as I vary the voltage, the line lowers as well.
Here I'm using the oscilloscope as most people do, to see periodic waveforms. The oscilloscope is graphing voltage versus time, where the time is set using a time base, in this case, 1 millisecond of time per horizontal division on the screen. Now imagine instead that instead of having a time base for the x-axis, you had a signal. And for the y-axis, you had another signal. That's what a Vectorscope is. It's a device that plots one signal as a function of another signal, rather than as a function of time. This particular pattern is from a pair of out-of-phase sine waves and is called a Lissajous figure. A Vectorscope helps you see the phase relationship between two signals. And you can get some wild-looking patterns. However, this Vectorscope is intended to display the phase relationships between the chrominance signal versus the color burst signal in a color TV, so that the chroma demodulator circuits can be properly aligned. That's a mouthful. Let's take apart this Vectorscope and see what's inside.
There are 6 screws to be removed on the front, plus in the compartment at the back which holds the cables, there's 1 screw in the middle there, plus 2 in the bottom, and then the whole chassis slides out.
Inside is a very compact cathode ray tube and 2 miniature tubes. Also clearly visible are a number of paper capacitors and an aluminum electrolytic can capacitor. All these will have to be replaced before I can use this Vectorscope. There are also a number of potentiometers on the side for calibration. A visual inspection reveals that somebody else has been in here before me, and I don't like their work. This will have to be fixed, but this also means there may be more bodge modifications elsewhere. This is always a possibility with old equipment. I have 2 schematics for this Vectorscope, one dated August 1966 and the other dated February 1970, which gives some clue as to when this was on the market. However, I found that my unit doesn't exactly correspond to either schematic. It's a little of both, though much closer to the later one. The differences are related to some of the component values. Also, the earlier version had different deflection circuitry, driven by a second 12AU7 tube, and had provision for a 350 volt supply, not present in the later one. The first thing I usually do is test the tubes. If the transistors are socketed, I pull them and test them as well. In this piece of equipment, the transistors are not socketed. Both sections of both tubes test very strong. The next step is to start replacing the electrolytic and paper capacitors and cross them off the diagram as I go. As I replace capacitors, I check nearby carbon composition resistors to make sure they're within tolerance. Then I cross them off. Carbon composition resistors are notorious for drifting, usually higher in value. It's always a good idea to measure their resistance.
I've finished recapping the top surface of this unit. The CAN capacitor that was right here, I don't keep except in old radios, in which case I just keep them for appearance only. But for a piece of test equipment, I don't bother.
A terminal strip with electrolytic capacitors mounted on it is fine, and I certainly wouldn't bother restuffing them.
I decided to take out the picture tube to give me better access to, well, everything. If you do decide to do that, make sure you mark the top so that your sweep is not tilted later on. It's held in really by the bezel and by the neck. It's not difficult to take it out, just don't over tighten it when you put it back in because the result will be catastrophic. That leaves the bottom, which is going to be challenging in a few places, not just replacing but also making sure everything is tested.
If you see disc capacitors with cracks in them, they're not cracks, they're spark gaps.
I didn't think I'd finish today, but I have. All the paper capacitors and electrolytic capacitors have been replaced, and most of the resistors have been checked, and most of them are okay.
Gently clean the wipers and contacts on all rotary switches with isopropyl alcohol and cotton swabs. They will have many years' worth of tarnish on them. Be sure to use deoxit control cleaner on all potentiometers to make sure they operate smoothly and the resistance elements don't have any dead or iffy spots. The first time base uses a transistor as a 189 kHz crystal-controlled oscillator. A pair of transistors divides this frequency by 6 to produce the 31.5 kHz signal. The 31.5 kHz signal is divided by 7 to produce a 4.5 kHz signal. That is divided again by 5 to produce a 900 Hz signal. The 900 Hz signal is divided by 15 to produce a 60 Hz signal, which is the vertical sync signal sent to the mixer. The 31.5 kHz signal is also divided by 2 to create a 15.75 kHz signal, which also goes to the mixer. The output of the mixer is a composite video signal, which is amplified by 1/2 of the 12AT7 tube to produce the video output in both polarities. The other half of the 12AT7 is an RF oscillator running at TV channel 3, 4, or 5's frequency, modulated by the composite signal to produce an RF signal output. The second time base uses 1/2 of the 12AU7 tube as a crystal-controlled oscillator running at 3.563 MHz. This signal is fed to the color keyer, which is mixed with the 189 kHz signal. This gives bursts of the 3.563 MHz signal. This is the color signal available at the pattern switch. The signal inputs, whose phase the Vectorscope is actually measuring, are the TV's red CRT grid and the TV's blue CRT grid. The accelerating voltage for the picture tube comes from a voltage doubler circuit and produces about 600 volts at low current. A single wave rectifier at the transformer produces 125 volts DC for the plates of the 12AT7 and 12AU7 tubes. This 125 volts is further reduced and held to 18 volts by a shunt regulator, which is just a Zener diode.
This is my test setup. I've got the Variac ready to go. I'm going to be measuring two voltages in the circuit, V plus 125 and V plus 18. what I measure should be directly proportional to the input voltage. Okay, power on. Yep, we're getting something. So this is a V plus 125, and this is V plus 18. So this should top out at 18 because there's a center diode in the circuit. So far, so good. So we're at about 20 volts or something. Input is 110, and I'm getting 124.0, that's fine, and 17.6, which is fine. The intensity is all the way down, as it should be. Yep, I have a green dot. It's not focused, but that's what focus is for. There we go. And I should be able to change the position of the dot. Get it to where it needs to be, the middle, and then it can serve as a vectorscope.
At this point I can be sure that I'm getting the proper voltages, including the acceleration voltage, and that the CRT works. I will still have to check the frequency calibration as well as the deflection circuitry. That will be in part 2, because I don't want this video to get too long. I hope you enjoyed this video from Mr. Brown's Basement. Please like and subscribe to be notified when new videos come out. Also, feel free to leave comments, which I'll do my best to respond to promptly. As always, thanks for watching.